You are welcome to FANOG Research Group YouTube channel. Please click on the subscribe button to subscribe to our YouTube channel. You will get notified whenever new video is uploaded.
So if you recall, we have we've defined the inner product space, and we've also spoke about the the Hilbert spaces. Hilbert spaces are complete inner product spaces. Okay, Hilbert spaces are complete inner product spaces. Okay, complete inner product spaces. That's what a Hilbert space is. And we gave examples of Hilbert spaces. All you need to show that a space is Hilbert is to show that the inner product space is complete. You know, every complete inner product space uh, is is a Hilbert space. So all you need to do is to pick up an arbitrarily Cauchy sequence and show that that space, Cauchy sequence converges to an element, and that element is in that space under consideration. And once you can do that, then the job is done. Okay? So that's completeness. Of course, there's a whole lot of theories built on that. Okay, there are theories built on that. We are going to that are built under that. I hope you can hear me, Meratu. Can you hear me loud and clear? If you can hear me, let me be sure that you can hear me. Okay, okay, that's fine now. Okay, yeah. So let me now share some of the theories that I want to look at today. Theorem says let H be a Hilbert space, and let K be a closed convex subset of H. Subset of H. Then K contains a unique vector of minimum norm. Okay, so that's exactly what that theory is saying. So if you have a Hilbert space, H, a Hilbert space, and you have K to be a convex, K is a subset of H such that K is convex. K is convex and closed. K is convex and closed. I'm sure you remember when a set is said to be convex. A set is said to be convex, if you recall, if X, Y is in K, and you have that for lambda between 0, 1, you have that lambda X plus 1 minus lambda Y, that's lambda X plus 1 minus lambda y is also in K. Okay, so that's convexity. I'm sure you recall that. And if a set is closed, uh, if it's closed, it then means that it contains all of its limit points. So K is such that K is convex, meaning that this condition is satisfied, and K is closed also. Uh, Closed subset of H means that K contains all of its limit points. Then, with that, the following consequence will follow. K contains a unique vector of minimum none. We are going to try to do some construction of the proof. Maybe from the construction, you likely make more meaning out of this. So let me go to the construction um, of the proof of this theory. Okay. Um, Proof. Proof. Um, if you let delta to be the infimum of norm of x. Of course, your x is an element of K as we are defining it. If you now let a sequence, call it Xn, to be a sequence in K, such that that sequence, the norm of that sequence, norm of Xn, converges to delta. I'm sure you recall how delta is defined. Delta is defined as the infimum of norm of X, such that S is in K. So if you have a sequence in K such that that sequence converges to delta, so defined above, okay? If you use, because you are in a Hilbert space, so you can use every Hilbert space that satisfies the parallelogram law. I'm sure you remember the parallelogram law. So using, since you are in Hilbert space and Hilbert spaces satisfy inner product spaces satisfy parallelogram law. So using the parallelogram law, as well as the convexity, because K is convex. And kind of explain what convexity of a set mean. So convexity of K, then we have the following estimates. Okay. What do we have? We have the following estimates. I share a new slide. I share a new slide. Um, I share a new slide. We have the following. Uh, Using parallelogram law, you have norm of, remember you are dealing with the sequence xn. And this sequence xn, you can begin to talk of it being Cauchy. So you have norm of xn minus xm. There, by parallelogram law, you can do this. Norm of x squared is equal to 2 into norm of xn. I'm sure we are just quoting parallelogram law. Norm of x squared plus norm of xm all squared, okay, minus 4 into norm of xn plus xm plus xm. If I can do this over 2 over 2, of course, you complete the norm, all squared. Okay, the whole of this goes to 0. Okay, the whole of this goes to 0 as mn goes to infinity. Okay, why? Why? Because these are objects in K. These are objects in K. Xn plus xm over 2 are in K. They are objects in K. And you have that norm of, because I'm sure you recall how xn is defined. Xn tends to delta. Okay. So you now have that um, norm of, I mean, let me close some wanted notifications. Okay, that's fine now. Uh, so you have that norm of xn plus xm over 2 norm. This is greater than or equal to, because each of them is going to delta, so this is greater than or equal to delta. Okay. And what's the conclusion? The conclusion is that this sequence is Cauchy. The sequence xn is Cauchy. Okay, it's Cauchy. Let me share a new screen so that it will be neater. Um, the sequence xn is Cauchy. Xn is Cauchy, and if it's Cauchy, of course, in K, because these are sequences in K. And since K is closed, you can be sure, since K is closed, then you can be sure that the limit of xn is in K. Okay? Limit of xn is in K. Um, so you now see that K is complete. Is complete. Now, we can say, since xn is a Cauchy sequence, you can as well say that xn converges to x star, okay, to x star in K, in K. So our job now is to show that x star has a minimum norm. So we show that x star has a minimum norm, has minimum norm. I'm sure you recall how that norm was defined. Delta, that was the delta, I think in the first slide. But if you can't recall, let's recall it now. I share a new slide, and We go back to that. Um, what that means is that you have the norm of X star will be equal to norm because it's this limit is the limit of a Cauchy sequence, so limit of xn actually. Okay. Of course, limit can go out of norm. That's one of the properties. So here you have limit norm of xn, and we already know what this norm is all about, this delta. Okay. What's the meaning of that? You now see this implies that x star has minimum norm. Of course, the next thing, remember that that theory says it has unique minimum norm. So if it has minimum norm, the next to show is that this X star is unique. So next, we show that X star is unique. We show that X star is unique. What does that mean? It then means that if there's another object or another limit different from X star, maybe you call it U different from X star. Okay, our job is to show that both U and X star is the same. Okay, so uh, if you say that U is different from X star, such that norm of U, because norm of X star is delta also, so yeah, norm of U is also delta. If that is the case, then what you are simply saying is that uh, since they are not the same, so zero will now be less than their difference. If they are not the same, zero will be less than their difference, which is that norm of X star minus U. Okay, zero will be less than that. So which will be equal to, if you recall that parallelogram law, 4 delta squared minus 4 norm of if you recall the other one, that's S star. We are just putting this back to that parallelogram law plus U plus U all over 2, if you recall. Norm, norm. All of this is squared. I'm sure you remember. Let me share a new screen so that we can now continue the computation. So you have the following. You have the following that norm of X star plus U over 2, that norm is less than delta. Remember that K is convex. K is convex. What does it imply? This implies that this must also be in K. In other words, you have that X star plus U all over 2 must also be in K. Now, this is a contradiction. This is a contradiction. And why that is so is because you initially assume that U and X is different. So the next thing is the right assumption is that U is actually the same thing as X star. So hence the limit, which is X star, is unique. Is unique. Okay, so that's that theory. Um, the next theory we'll be looking at is what we call the John Jordan von Neumann theory. Jordan
Hello.
von Neumann theory. Yes,
Could
I
you
can hear you.
explain again about the contradiction?
Okay. Look at this. You know that this x star plus u is in K. That's
Yes.
from all that we have said. And now this is a contradiction because look at the beginning. If I go back to the other slide, recall that we said that this x star and u star, x star and u is different.
Yes.
We said that x star coming x star, sorry, let me share. Sorry for I think trying to delay. Okay. Uh-huh. Recall that we said, okay, I think it's not this slide. Let me go back. It's not this one. Uh, Let me go back. Okay, I think it's this one. Let me go back. I'm trying to go back so that we can see that. Okay. So recall that we said that um, U is different from X star.
Yes.
Okay.
Yeah.
Now, if U is different from X star, uh, the meaning is that, and K is convex, K is convex. So you now have that lambda U plus 1 minus lambda uh, X star, X star um, is is in K. So look at this. If X star and U is the same, okay? If X star and U is the same, so what you now have is that lambda X star plus 1 minus lambda, 1 minus lambda X star, because they are the same now, so that you can now factor out, you can now, since they are the same, X star and S star is common. So you now have, if I come down here, you have X star into lambda plus 1 minus lambda. Okay? So you now see that here you just have X star only. Okay? But here, instead of having X star, you have X star plus U. Okay, you should have got X star plus X star, which will be 2X star over 2, which will now be X star. I don't know if you understand in K, but instead of that, you have this one. Okay? So, which, because it's convex, for it to be convex, you now discover that this must be equal. That's what I'm trying to say. So our result with all that we have done should have been X star in K, but we got X star plus U over 2. Okay? So that's why it's a contradiction. I don't know if you really understand what my explanation.
Lambda x star
Yeah.
plus 1 minus lambda.
He said?
Is that lambda x star plus 1 minus lambda x star? Is that above 1?
Yeah, exactly. Lambda plus 1 minus lambda. Of course, lambda we cancel minus lambda. You are left with 1 so that you have only x star. Okay?
So why, if
The
since u is different from x star, why we substitute u is equal to x star now?
No, here, remember at the beginning, we assume that u is different from x star. That's at the beginning. I don't know if
Uh,
you understand what I'm saying. Now,
okay.
but remember, this is a convex case. For it to be convex, this have to happen. You know, u x star plus u over 2, okay, is in K.
Mhm.
So if that is the case, it then means that x and u is the same. So that if you now put if you put that substitution into the convexity equation, you have only one extra, not just this one. It's because
Okay.
of you are taking consideration of the convexity as well.
Okay. Thank
That
you,
is
Prof.
what is okay. So let's look at the other theory, and then which is the John Newman von Neumann theory. I'll share yet another screen, and then we proceed. Okay, yeah, okay. Theorem. This theorem is called Jordan uh, von Neumann. Okay, and it states the following: the norm of a normed linear space non-linear space E is given by an inner product, if and only if and only if the norm satisfies the parallelogram law, that is, for arbitrarily vectors x and y in E. I want to, instead of continuing here, I want to show the next equation is here, which is norm of x plus y, norm of x plus y squared plus norm of x minus y, the parallelogram law, x minus y squared is equal to 2 into norm of x plus norm of y. This is squared. I'm sure you know that. Plus norm of y all squared. So the norm of a non-linear space E is given by an inner product if and only if the norm satisfies the parallelogram law. So, which of course is this the parallelogram law? So that is the Jordan von Neumann theory. Okay, it's a necessary and sufficient condition, if and only if. So if you have the norm of a non-linear space given by an inner product space, you can show that it satisfies the parallelogram law. And conversely, if the norm satisfies parallelogram law, you can show that it's given by an inner product space. So that's the John von Neumann theory. And of course, this theory is highly useful. For example, when a non-linear space is not an inner product, it's you now discover that you just show that the norm defined on the space does not satisfy the parallelogram law. So that's that. So if it's not an inner product space, you just simply show that it doesn't satisfy the parallelogram law. That's the usefulness or the application of this theory. Okay, so let's proceed to some other concepts. The autonomous sets. Also autonomous sets. Okay. Of course, as a new concept, we need to define certain things. Two vectors, x and y, in an inner product space E are said to be autonomous that is written as follows: x pap y, x pap y. That's the way it's said. Or you can also say y pap x. Okay, look at the way it's read. You say x pap y or y pap x. Okay, and if you have that the inner product of x comma y is actually 0. Okay, now if M is a subset of E, then we write that I'll write it here. Write that x pap m s pap m if you have that x pap y for all y in M. Okay, so I need us to go through the definition once again so that we can make more meaning of this. Two vectors x and y in an inner product space E are said to be autonomous. In other words, x pap y or y pap x. Those are the two vectors. Okay, if they are said to be autonomous, if the inner product of x comma y is 0. Now, if M is a subset of E, I'm sure you know what E is. There are the inner product space. Okay. So if M is a subset of E, then we write that X pap M. Pap M. For X to pap M means that if you pick up any Y in M, X will pap that. In other words, the inner product of X and Y will be 0. This kind of, the angle between them is 90. I'm sure you know that. The angle between them is 90. So that's this simply geometrical interpretation of that. Okay, so let's have the following remark. This is just autonomous sets definition. So let's have a remark on what we just said now. Remark since you have the inner product of X comma Y is the same thing as, if you remember, one of the properties of inner product Y comma S, but they conjugate. Now it follows that the X pap Y, if and only if and only if Y pap X. Moreover, you have that X is also perpendicular to itself. So X pap X, if and only if you have that X is a 0 vector. Okay? And of course, X pap 0 for all X in E. So these are the remarks. So X is pap to 0 for every X. And not only that, X is pap to itself, if and only if X is a 0 vector. So those are the remark. We give yet another definition. We give yet another definition. Definition. A set S is an inner product space. An inner product space E. A set S in an inner product space E is called an orthogonal. Remember what we discussed before was orthonormal. So this one is orthogonal. Orthogonal sets, if you have that the inner product of X comma Y is 0 for each X, Y in X, and X different from Y, the set S is called orthonormal if it is orthogonal sets. If it is orthogonal sets, And you have that the norm of x is 1 for every, I have that the norm of x is 1. And that will happen for every vector for all vector x in S. So let's go through that definition again. A set S in an inner product space E is called an orthogonal set if the inner product of x and y is if the inner product of x and y is 0. I think we wrote that very well. For every x and y in S. And of course, x is different from y. Now, the set S is called orthonormal if it is orthogonal set, and not only that, if norm of x is 1. Norm of x is simply the length of x from the origin. The length of x from the origin. That's the norm of x is 1. So the length of that from here to here will be 1. Unit 1. Okay? So that's the geometrical interpretation of that. Okay? So we give some examples in some spaces that we have already discussed. Okay, so let's try to give some examples. Example. In L2, we have S to be En, this vector that are infinite dimensional and is given by, of course, E1. You have the first dimension, 1, 0, 0, infinite dimensional, so it's not going to stop. E2, you have 0, 1, 0, 0. Of course, it will not stop. If you continue like this to En, En is, just continue like that, 0, 0, so on and so forth, 0, 1, 0. Now, this 1 is in the nth position. This 1 is in the nth position. Okay. So, of course, you continue like that. You continue like that. This set is an orthonormal set. This set is orthonormal. An orthonormal set. Okay. Okay, we have another example also. Another example. Example. This one is in capital L2. In capital L2, 0, 2 pi. Okay, in that space, the set S, which is equal to 1 over root 2 pi, 1 over root 2 pi exponential int. Of course, this is like a sequence counting from n equal to 1 to infinity. This set is also an autonomous set. Okay? So those are examples of autonomous sets. And then there are results that are, that characterize this type of sets. So let's now produce some of them. Some of the results that characterize this type of sets. I call it proposition. Let S be an autonomous set in an inner product space. Inner product space E. Let the following finite dimensional vectors U1, U2 up to UN. This be a finite subset. Be a finite subset of S. Then, if that is the case, then you have that for any vector X in E, for any vector X in E, you have the following. You have that the summation, I write it here, summation, because it's finite dimensional, I counting from 1 to n of the modulus of the inner product of X and all the UIs. I'm sure you remember all the UIs, U1, U2 up to UN. So of all the UIs, in other words, they are talking of the modulus of all of this is less than or equal to norm of X all squared. Okay? So that's one of the theories over there. The proof is also not difficult to verify. I give you yet another result also. So usually some of these results, you see, helps us to, kind of, put this into some inequality that will help us to estimate whatever we are looking for, approximate whatever we are looking for. If, for example, you have S to be an autonomous set, and that autonomous set is defined in an inner product space, then if you have a finite class or subclass of S, then for any X in E, you can actually do the following. The modulus of the inner product of X as well as that finite subclass will not go beyond the norm of X all squared. So that's the estimates. So Very important results, highly applicable in literature. Okay, so let's give yet another result. We give yet another result. I call it, sorry, for that, I share it again. Trying to share it again. Okay, maybe I get a new screen. Okay, fine. Okay. Okay. Trying to share the, let me use this one. Okay, that's fine now. Sure. This theorem is known as Bessel inequality, yet another estimation, Bessel's inequality. It states as follows. If this time around you have infinite, this is like a sequence of course, a sequence takes values from the entire natural number system. If this is an orthonormal, these are orthonormal sets in an inner product, inner product space E, then for every arbitrary vector x in E, we have the following. We have that the summation I running from 1 to infinity of the modulus of inner products of x and ui. This modulus is less than or equal to norm of x squared. Okay. So that's for that. Now we are trying to look at the whole lot. Of course, where we are going to, we want to look at some special class of operators. And once we do that, like self, adjoint operators, normal operators, unitary operators, well, all these terminologies are very important. And once we look at all of those, I think we go into optimization and then we begin to round up functional analysis. Okay? So that's our attention. Where are you now in your tutorials with Dr. Francis? Which topic are you now?
Hello, Prof.
Yes, I was asking with Dr. Francis, tutorials, which topic are you dealing with now?
Now, I don't know exactly, on Monday, I have a connection problem, so I didn't attend the class.
Okay. Okay. It's okay. It's okay. So,
but I hope we start to see concepts of Banach space.
Banner space. Okay.
I think
It's okay. That's fine. That's fine. Let's go to the projection theorem. The projection theorem. Um, Now, in an inner product space, there are some theories or some questions that are very important. If E is an inner product space and M is a subspace of E. Now, if you have an arbitrary vector in E, we consider the problem of finding a vector M star in M, which is closest to E. Okay, what I mean is that if you have an inner product space E, an inner product space E, and M is a subset of E. Okay, so you have that if you pick up an X, I'm sure you know that since this one is bigger than M. So if you pick up an X in E, okay, there's this problem of finding an element, maybe we call it M star in the subspace of E, which is M star in M, okay, which is closest in a way, which is closest to X, okay, in the sense what we mean that uh, that norm of X minus M is minimized. Okay, that's what we mean. So it's always it's a problem. Norm of X minus M is minimized. Okay, or M star rather. I think we picked M star is minimized. Okay, so let's that's always that question. Let me formalize the questions, and then with that we can begin to formally formulate a theory that will help us to provide an answer to those questions. Okay. The questions are as follows. Question. If I call this question 1, question 1 is as follows. Is there actually a vector M star in capital M which minimizes norm of X minus M over all M in capital M? Is the question. Or small m in capital M. So it's a question. Question 2 is that if the answer to number 1 is yes, that is if affirmative. If answer to 1 is affirmative, then the next question is that such is is affirmative. Let me go to the next slide so that we'll be able to clearly write that question. Okay. Question 2. If the answer to question 1 is affirmative, the question is M star unique? Do you have at most one M star? Is M star unique? The last question now, question 3. These questions will lead us to some beautiful results. Now, if a unique M star exists, if a unique M star exists that minimizes the norm of x minus m, how is M star characterized? How is M star characterized? So these are the basic questions. How is M star characterized? Is a question. So now the answers to these questions will be given in the following theorem. Okay, remember question 1, based on the fact that we have that if you are in an inner product space and M is a subspace of it, and then you are looking at picking up a vector of X from E and picking up M star from M, and then you are looking at the minimum norm, which is norm of X minus M. So those questions that arise, number 1 is there actually a vector M star which minimizes norm of X minus M over all M in M? And number 2 is that if the answer is yes, the question is M star unique? In other words, is it just only one M star? And lastly, if M star is unique, exists, which minimizes norm of X minus M. Now, how do we characterize such M star? So those are the questions, and those questions will be answered by the following theorem. Okay. Theorem. Let E be an inner product space and capital M be a subspace of E, and you have that the vector X can arbitrarily arbitrary vector in E. Then, if there exists a vector M star in M, in capital M. I'm sure you remember capital M is a subspace of E. Okay, in capital M, such that I put equality here. Norm of X minus M star is actually equal to, equal to infimum of, as X, M varies in M, small m varies in capital M, of norm of X minus M. Then I continue here. Then M star is unique. M star is unique. M star is unique. In fact, M star which is in M, capital M, M star which is in capital M is a unique minimizing vector. It's a unique minimizing vector. It's a unique minimizing vector if and only if you have that X minus M star pap capital M. I'm sure you remember this. Okay, so let's see that theory again. We understand it. I think we'll now round up today's class. If E, let E be an inner product space and capital M be a subspace of E, and X is an arbitrary vector in E, then if exists a vector M star in M, remember X is in E, while M star is in M. So if you have such vectors such that the norm of X minus M star, X in E, M star in M, is equal to the infimum. Infimum is I'm sure you remember in reanalysis, that's the smallest, the minimizing kind of set. So the infimum as M varies in M, norm of X minus M. Then you now have that M star is unique. M star is unique. Now, in fact, M star is a unique minimizing vector if and only if X minus M star pap capital M. So that theory, possibly by next class, we'll be looking at the proof. But this theory is one of the very important and highly applicable theory in the whole of function analysis. It helps a whole lot in finding. In optimization, M star is like the minimizer. Okay, it's like the minimizer. So that's the class for today. I don't know if you have any question for us. By next class, we should be going deeper into optimization. So I don't know if you have any question.
Okay, no question.
Okay. So thank you. We'll be meeting on Saturday, 1 to 3.
Okay. Thank you, Prof.
Yeah, sorry. Yeah, sorry for the interruption at the beginning. I think we had a lot of network issues. Yeah, thank you very much.
Thank you. See you.
Yeah, yes.